Alright, so today we're looking at lesson 55, circular unbanked tracks and two parallel resistors. So hopefully after this lesson you'll understand circular unbanked tracks and two parallel resistors. We remember if we have an object that's traveling at a constant speed along a circular path, a centripetal force is required to give the object an acceleration towards the center of rotation. We've already talked about centripetal force a couple weeks ago. But if you have an object going at a constant speed around a circular path, centripetal force gives the object an acceleration towards the center of the rotation, towards the center of your circle. The centripetal force required to keep the mass moving in a circle is going to be provided by the tension in the string. So the tension in the string is where the centripetal force comes from. These are the two equations that you use to compute the required centripetal force. So you have mv squared over r and mr omega squared. The book says it is a good idea to repeat these out loud several times a day until they become familiar as F equals ma. So you can repeat those out loud several times a day until they become as familiar as F equals ma, or you can just add them to your note card, whichever you think would be better for yourself. Okay? If you have a car that is driven on an unbanked circular track, the centripetal force is provided by the static friction between the tires and the surface of the road. So if it's unbanked, your centripetal force is provided by the static friction between your tires and the road. We will later look at banked circular tracks. If you're not sure what unbanked and banked means, think about a NASCAR track. It is always going to be banked as they go around the curve. It means it's like at an incline. It's tilted. And that's to help keep the car from just sliding off the bank, off of the track. Think about on interstate, if you're getting off at the mall exit. I know a lot of y'all don't come from West Monroe to the mall. Y'all are coming from the opposite direction. But if you are coming from West Monroe and you're getting off at that exit and you're going to go take a left and go over the interstate and Lowe's is over there on your right, that ramp right there is banked. It's at a tilt. It's at an incline a little bit so that your car doesn't just slide off the side of it. So that would be an example of banked. We're looking at unbanked. So that means that they are flat. This would be driving down a road and you're turning. There's no tilt or slant to the road. It's completely flat. Okay? So let's look at an example. A level circular track has a radius of 100 meters. A 1,000 kilogram car moves around the track with a constant speed of 30 meters per second. What coefficient of static friction between the tires and the track is required to keep the car from sliding sideways? All right, so we start by finding the centripetal force for this problem. And so we're going to start with one of our formulas. We're going to use mv squared over r. And the reason we're going to use this one, they did not tell us our angular acceleration, our omega. So we don't want to use that formula. So our mass is 1,000. Our velocity is 30. And our radius is 100. And so if you multiply this out, you end up getting 9,000. Okay, so that is our centripetal force. Now, whenever we have an unbanked track, a level circular track that's unbanked, the centripetal force equals the same thing as the static friction. So our centripetal force equals our static friction. And the static friction is given by F sub n and then mu sub s. We talked about that way at the beginning of the year. And so we know that our centripetal force is 9,000. F sub n is just your mass times your gravity. So our mass is 1,000 and our gravity is 9.81. And then we're solving for mu sub s because that's the coefficient. Whoop, that's the coefficient of static friction here. And so if you solve for your mu sub s, you end up getting 0.92. And there aren't units on that. That's just 0.92. And so that'd be your answer there. Okay, looking at another example, the coefficient of static friction between the tires of a car and a track is 0.820. What is the maximum speed of a 984 kilogram car can attain without sliding on an unbanked track whose radius is 125 meters? So we're going to start with our centripetal force formula, mv squared over r, and we're going to fill in what we can. We know that the mass is 984. We are looking for the max speed, so we don't know our velocity squared, and our radius is 125. And so that is your centripetal force. And if you simplify that, you get 7.872 times v squared. And now we know that our centripetal force and our static friction are related. They're equal to each other. So we're going to find our static friction using this formula. They tell us that the mu is 0.820. And so our Fn is our weight, 980, our mass, 984, and then times 9.81, and then times 0.82. I ran out of room right there, but that should say 0.82. I'm going to rewrite it for you. Okay, and so if you multiply that out, it gives you 7,915. And so that is what your centripetal force can equal. So we have 7,915 equals 7.872 velocity squared. And so if you solve for your velocity, you should end up getting through 31.7 meters per second. And we have 3 sig figs, and so that's why we go to set 31.7. Okay, so that's how you deal with unbanked tracks. Your centripetal force is just going to equal your static friction. Now looking at 2 parallel resistors. We know that the reciprocal of the equivalent resistance of resistors in parallel is the sum of the individual reciprocal resistances. We looked at this formula a couple weeks ago. 1 over r sub e equals 1 over r sub 1 plus 1 over r sub 2 plus 1 over r sub 3, etc. All the way until you end up with all of your individual resistances. That was the formula. We often encounter 2 resistances in parallel, and there's an easy way to find the equivalent resistance of 2 resistors in parallel. It's given by this formula. The equivalent resistance of the 2 would be R1, R2 over R1 plus R2. And they show you pretty quickly how to solve for that in the book on page 381. But basically, that formula I just wrote a minute ago where we had R1 1 over r sub e equals 1 over r sub 1 plus 1 over r sub 2. You just solve that for r sub e, and you know how to do that algebraically, but that's how you end up with the formula that's written at the bottom. Okay? So if you look at this example, we want to find I sub 1. So what we need to do first is to find the equivalent resistance of those two that are in parallel. So we're going to use our formula. R sub E equals R1, R2 over R1 plus R2. And so our R1 and our R2 are 10 and 20. So we have 10 times 20 over 10 plus 20. So the 10 times 20 is 200 over 30, and so that's 6.67. 6.6 repeating technically, but they rounded it just to 3 decimal place, 3 sig figs. Okay, so that is our resistance, and the units, whoops, look like that. So now we are going to use our V equals IR. We know our voltage is 50. We are looking for the I, and we know that our resistor is 6.67. And so if you divide that, you end up getting that your I is 7.5 amps. And so that would be your answer there. So it's a parallel resistor problem that we've already done. It just makes it a little bit easier because we have that equivalent resistance formula. Okay? So your homework is 1 through 20, and the curveball questions 1 through 5. Make sure to look over those. Make sure that you do that tonight so that we can go over any questions that you have tomorrow.